Thanks a lot. It's really a great pleasure and honor being here, and a big thank you also for the distinguished lecture award. This really was a big pleasure, is a big pleasure. And by the way, so my physics teacher was present yesterday at the at the event, so which made it sort of special. Now, the question I would like to address today is the one you see here. How does a quantum optic gravitate? Let me rephrase that a little bit differently. So what I really want to talk about it is how can we avoid the appearance of a classical world in gravity experiments? So paraphrasing one of Z's famous ways of talking about decoherence. Now, we are celebrating 100 years of the famous works of Heisenberg, Born, and Jordan, the origin of quantum mechanics as we know it. And what we also should not forget when you talk about 100 years of quantum physics is that around that time, another theory of physics, namely the theory of gravity, was co-developed at that time. And this co-development happened to some extent even by the same people. And obviously, there has been a connection ever since from on the table between those two fields from early on. And I just want to give you two examples in the pioneering work of Einstein 1916. This is the paper where he sees for the first time that his theory of gravity actually produces gravitational waves. He makes the observation that not only when electrons move do they radiate electromagnetic radiation, they also have to radiate gravitational radiation. And he writes in his 1916 paper, as a result of the internal atomic movement of electrons, atoms must radiate not only electromagnetic, but also gravitational energy, if only in minuscule amounts. Since this cannot be the case in nature because of the stability of matter, the old argument, then it appears that the quantum theory must modify not only Maxwellian electrodynamics, but also the new theory of gravitation. So this is sort of the onset of the early thoughts of the interplay of quantum physics and gravity already in 1916. And then in 29, when Heisenberg and Pauli wrote down the first quantization of the electromagnetic field, they also write, it should be mentioned that a quantization of the gravitational field, which seems to be necessary for physical reasons, asterisk C, for example, Einstein 1916, where the necessity of treating the emission of gravitational waves quantum theoretically is emphasized, should also be feasible without new difficulties by means of a formalism. And so on. And you know how the story goes. Actually, the program was then completed in 1936 by Bronstein, who wrote down the first linearized quantum field theory of gravity, and then the rest is history. So even though we have early motivation for a quantum theory of gravity, that was built up extremely quickly, one has to say. Up to this date, we still do not have experimental evidence that gravity actually requires a quantum description. To put it in other words, we have quantum theories of gravity, but we don't know if we need quantum theories of gravity. This is essentially an experimental question that we have to ask to nature. The situation currently is the following. We have experiments to date at the interface between quantum physics and gravity, all of which can be described by assuming the joint validity of quantum theory on the one hand to describe the quantum system in experiment, and of classical gravity, namely general theory of relativity, on the other hand, to describe the gravitational field present in these experiments. Just very quickly, two of my favorite experiments. Here you have the famous cow experiment. Oops, where is it? Here you have the famous cow experiment by Colella, Oberhauser, and Werner, the initials of the authors, that explores the influence of Earth's gravitational field on a neutron wave packet. So the way they do it is they send a neutron through this single crystal silicon interferometer, and basically when a quantum particle, a neutron, traverses through a gravitational field, it acquires a dynamical phase, but this is of course a global phase. A global phase we cannot measure. So how do we measure phases? We can only measure phase differences. So we take the neutron, we split the beam up, we create a coherent superposition. One of the beams traverses at a different height of Earth's gravitational field than the other. So they pick up a gravitational field difference, meaning a gravitational phase shift difference. And after recombination and rotating the interferometer in Earth's gravitational field such that as a function of the angle, you have different height differences. You see gravitational induced interference fringes in the output of this experiment. So this is the first instance of showing the influence of Earth's gravitational field on actual matter wave packet in experiments. And this was the basis, of course, for later atom fountain experiments, atom interferometer experiments to measure Earth's gravitational field, and culminated in a recent beautiful experiment by the Kasevich group, where they showed the analog of the electrostatic Aharonov-Bohm effect in such experiments. Now, another one that I would like to show is gravitational redshift that you have here in the beautiful experiment by the group of Dave Vineland, where they demonstrated that when you take your experiment with an optical atomic clock, you lift it with the set of checks by 30 centimeters in the lab. You see that the clock rate of your experiment changes. And if you look in the literature recently, there have been two beautiful papers by Juniv's group and Simon Kolkowicz's group, where they now have sensitivities to changes of the clock in Earth's gravitational field on the sub-millimeter level. So this is our current experimental status that we have. Bottom line, quantum systems are extremely sensitive probes of classical gravitational fields, which is great. But the question is now, can we have experiments that a classical theory of gravity cannot any longer describe? And that was a question that was, to my knowledge, for the first time asked by Thomas Gold. He is an Austrian physicist who was present at this famous Chapel Hill conference in '57, who phrased it in more or less exactly that way. Feynman was also in the participant, and in his very inimitable way immediately stood up and said, yes, of course we can have such phenomena. And in order to produce such a phenomenon, what we need, and this is the content of my talk, is quantum sources of gravity. What do I mean by a quantum source of gravity? What I mean is we need, first of all, a system with sufficient mass that it produces a gravitational field. Then we take that system, let's say a center of mass, degree of freedom, and we put it in a quantum superposition. So what we have now is a superposition of gravitationally distinct states, meaning that the two possible states of the systems can be distinguished through a gravity experiment. So let's call that a gravitational cat state. So note already that the gravitational field distribution that such a cat produces is not any longer a valid solution of Einstein's field equation, so of a classical field theory of gravity. Now, the next thing that we do is we want to test now whether we do have a superposition of the gravitational field of the metric. How do we do that? Well, there's a simple test. You take a test particle here, a mass or a clock. The point is that your source mass produces a superposition of the metric. The test mass sees now as a consequence a superposition of geodesics. So in the time evolution, what happens is that the two systems become entangled through the gravitational interaction. It's as simple as that. So if the two states of the test mass become distinguishable after some time, then this overall state is entangled. So let me give you one example. You could take a clock also, instead of having just a mass and a geodesic. So for the clock, you can compute now the difference in the gravitational potential, and hence the difference in the gravitational time dilation that the clock experiences. And then you can ask, what is the clock precision I would have to have such that after a certain amount of time, I do get entanglement of the clock degree of freedom with my mass. And well, it's very simple to compute. And if I take, for example, my mass being on the order of the Planck mass, a superposition size on the order of 100 nanometers at a distance of 10 micrometers, of the two masses, I would need a clock stability, so precision of my clock on the order of 10 to the minus 32, which is still a few orders of magnitude away than what we have today. So we rather stick for now to the spatial instead of the clock degree of freedom. So summary being, entangling two systems via gravity cannot be explained by GR, meaning a classical field theory of gravity, because a classical field theory of gravity will, for such a mass configuration, always predict a fixed metric of space-time within which a test mass follows a fixed geodesic, meaning that the test mass can never become entangled with my source mass configuration. Now, this is something that, as I said, has already been pointed out in the early 50s. Now, this is the Chapel Hill conference, and Feynman made this very nice point. There exists, however, one serious difficulty, and that is the lack of experiments. Furthermore, we are not going to get any experiments. And then in this field, since we are not pushed by experiments, we must be pulled by imagination. So this was like the call to arms for the theorists to now come up to push the theory to the extent where you produce logical failures and theories break down in order to make statements. But luckily, what happened over the course of the next 70 years is an incredible development, of course, also in experimental physics, and what I call the advance of the era of macroscopic quantum physics, with increasingly macroscopic, more massive systems, of course, with many different fields of study, quantum many-body physics and so on. But for our purpose, what also happened is, with the advent of more and more massive systems, more and more ideas came up how to actually generate then quantum superpositions, then also of gravitational fields. There's a whole literature of different experimental proposals how these things could be done. Now, let's go into the details. The goal is now, for the remainder of the talk, to answer the question, can we produce quantum sources of gravity in the lab? Is this a completely crazy question, or is it something that has some possibility to be realized? So what do we need? We need extreme regimes, both of the quantum system, namely we need large mass, we need large delocalization, long coherence time, and of gravity experiments where we need short distances in order to push up the gravitation interaction, or in other words, it is actually the mass times the delocalization divided by d to the cube that defines the gravity gradient of the two different locations of your center of mass state that allows you to gravitationally distinguish those two states. In a nutshell, without going too much into the details, tomorrow there's still a technical talk. I will have more time to go into the actual details of many of the derivations. This is the condition that you need to fulfill in order to generate entanglement by gravity in such a configuration that I just pointed out to you before. You have your mass in a superposition with delocalization delta x, and then in order to generate entanglement, if both masses fulfill this criterion, the product of mass squared, delocalization square, coherence time, and 1 over d cubed, that's the distance for the gravity experiment, needs to be larger than Planck's constants versus over Newton's constant. If you manage to fulfill that criterion, you're in business. So this is what we investigate. I give you a teaser. How do you arrive at that expression? It's very simple. There are different ways of looking at generating entanglement. You could, for example, just have your two systems, your two masses, as quantum harmonic oscillators being kept next to each other. Delta x, the delocalization, is not just the extent of your Gaussian wave packets. The two couple with a 1 over r interaction. So you can write down your Hamiltonian if you want. You do Taylor expansion, and the first non-trivial entangling term is the XX interaction, which in two-mode quantum optics is a two-mode squeezing interaction, which generates EPR entanglement in positional momentum between those two. And writing it down in Hamiltonian formalism immediately gives you a coupling rate G, which tells you at which rate you create entanglement. On the other hand, an alternative way is to start off with two non-Gaussian states of your masses in a superposition of delta x, where delta x is now the distinctness in the center of mass degree of freedom in the cat states. Again, at a separation d, and what happens now is exactly what I told you before. You now have this gravitational gradient, you have the cow phase. So basically this mass here sees the two gravitational potentials of the mass being here and there. So you have now a phase evolution in the gravitational potential of this one here, which is essentially nothing else than a conditional phase gate now. So you have two qubits that are connected via conditional phase gate, and that generates entanglement if your initial two separable qubits have been prepared in superposition states. It also generates entanglement. And the interesting thing is, even though these two configurations look very different, the rate at which you generate entanglement is actually the same. So it's g over h bar, mass squared divided by d cubed times delta x squared. And of course, in order to generate entanglement, this needs to be larger than the decoherence rate. You rewrite that as 1 over the coherence time, and you arrive at our very simple expression up there. So that is the background. Now, you could ask now, well, then let's just go to Emmanuel's lab and let's just do it, because this is actually something that definitely one can easily realize in the lab. So let's put numbers. If we would have two atoms, you know, delta delocalization 100 nanometers, you will separate them by a micrometer and ask how long does it take to generate entanglement just through gravitational interaction. So we assume we can switch off and screen all electromagnetic interaction. Well, you can see it's 10 to the 24 seconds. It's like 1,000,000 times longer than the lifetime of the universe. If instead we go to solids, like two lead spheres, 50 micron in size, that's on the order of a Planck mass. We take a delocalization again of 100 nanometer, we separate them by 100 micrometer, then you see within 10 milliseconds, you generate entanglement. So this is the key to success. You need solid state systems. You need to cramp many, many atoms in a very small volume to generate a sufficiently strong gravitational gradient in order to create gravitational coupling that is sufficiently strong to generate entanglement. Now, I spare you the details. Again, if you're interested in those, tomorrow will be the intensive course on that. If I assume now that we have two spherical masses, both of which are now delocalized by delta x, are separated by d. I take typical densities of a regular solid, 10 to the 4 kilogram per cubic meter. I say that the surface distance between the two is in the order of 10 micron. I don't want to make it closer because many other effects will happen, and I want to put a Faraday shield between them to shield for the interactions. And I fix my coherence time to 10 milliseconds. Then, as you can see, it's sufficient. Well, sufficient. So the requirement would be, I would need to have a mass of 10 to the minus 4 times the Planck mass. So that's an object with a radius of 4 micron, with lead scale densities. And the delocalization has to be on the order of 400 nanometers. If I would be able to do that, if I have a 4 micron solid object, I delocalize it by 400 nanometers, so much, much smaller than the actual size of the object. And I have two of those and make them gravitationally coupled, then I would be in business. Within 10 milliseconds, I would generate entanglement. So question is this a ballpark number we can have in principle? Oh, and by the way, again, this is for details for tomorrow. Coherence time of 10 milliseconds in that case would mean that you need environment temperatures and particle temperatures on the order, so well below 10 Kelvin, and pressures below on the order of 10 to the minus 16 millibar. Okay, so let's start with gravity. Where do we stand? On the gravitational part, we are focusing now on this product. This is the nice thing about this expression. We can separate that now in gravity experiments and quantum experiments. So basically, we can do quantum experiments where we try to maximize this product. I want to do a single particle quantum experiment where I maximize mass times delocalization times coherence time. And then I do gravity experiments where I try to minimize d. Basically, I try to find out how close can I get to objects, small objects, and still only measure gravity as their interaction strength. Okay, so let's start with quantum experiments. Where do we stand with respect to this specific product? Well, let me give you a landscape of masses today in quantum experiments, and it's just a couple of nice pictures showing you that we have today in the physics literature experiments, and this is now systems where quantum states of motion, so really non-classical motional states, so spatial delocalizations of a center of mass degree of freedom have been demonstrated, ranging from single atom systems up to bulk solids, where we have the collective motion of up to 10 to the 18 atoms in an acoustic mode of such bulk acoustic resonator. So this is the span that we are talking about. And as you can see, there's quite a large range from a billion atoms up to Planck mass number atoms, 10 to the 18 atoms, in the domain of solid state densities. And I just very briefly mentioned that this is sort of part of a development that now goes back to more than 20 years. And that goes back even more than that. So coming from Vienna, I need to point out Schrödinger's role in that. So it turns out that already in 1931, Schrödinger wrote to Sommerfeld that basically he was complaining about those fundamental questions. So he writes in his letter, oh, those fundamental questions torment me more and more. And I would like to show you something that we discussed in our seminar. And then he makes this drawing. You see, is this thing here where it says schwerer Spiegel, heavy mirror. Yeah, and then this thing, it says Lichtquant, so photon. So basically, he describes now to Sommerfeld that they discussed the situation where the photon hits the mirror, and then, oh, so strangely, you can use now the mirror as a measurement device for the properties of the photon. And if you do that, then it turns out that the product of the conditional variances of X and P of the mirror violate Heisenberg uncertainty. And isn't that strange? Now, today we know this is actually a quantitative measure for continuous variable entanglement. And Schrödinger wrote that down already in 1931 before he coined the term entanglement. So it's very funny. Anyway, so I think this is the early motivation for using quantum states of light to control quantum states of motion. And we had that already in the previous talk. This is something what then happened, like I would say more than 20 years ago. I think Mike Rukas was one of the pioneers who really put out this mission. We want to put mechanics into quantum mechanics. And what you see here is one of our early attempts of a little diving board. We did this together with Keith Schwartz's group back then at Cornell. Where then just using radiation pressure on those mirrors, we were able to control the motion of those objects. And essentially what you do is, well, many of you know that it's more or less, it's a Raman scattering process using a cavity to resonantly enhance the anti-sideband, so the anti-Stokes scattered photons in order to cool the system. So what you have here is our early attempts where we basically just took a Thorlabs mirror, we micro machined into the mirror these little cantilevers and under etched them. And so basically pointing the laser here, what you see here is the TM00 mode, just of a Fabry-Perot cavity. The back mirror could move, and then by just detuning the cavity, we could then laser cool the center of mass motion. And back in 2006, so again, almost 20 years ago, there was a modest factor of 30 in cooling from room temperature. And then we managed eventually in collaboration with Oscar Painter to go all the way down into the quantum regime, showing that you can use methods of laser cooling of radiation pressure interaction to have quantum control over the center of mass degree of freedom of such solid state macroscopic objects. And that evolved into now many groups worldwide being able to manipulate and control quantum states of motion up to the regime of Planck mass scale acoustic oscillations in those resonators. So let me come back now. This was the question. What about where do we stand with respect to this product? Here, atoms and macromolecules is something you have all seen and heard of. So this is Markasiewicz's experiment with the half-meter superposition of a single atom, and then Markus Arndt's experiments in Vienna with macromolecules with 2000 atoms in superpositions on the order of 500 nanometers in the grating. If you put the numbers, you see in that case, the product of mass, delocalization, square, and current time is 10 to the minus 12. And this is now in units of h bar over g. And assuming an hypothetical distance of the center of mass of the two systems of 10 micron, so it should be 1 in order to create entanglement. Well, so for the atoms, it's now not really surprising. For the molecules, it also doesn't work. We are falling short 19 orders of magnitude. So let's go to our solid state objects. For the solid state objects, you see, this is a beautiful recent result by Yiwen Chu's group at ETH. Again, this so-called bulk acoustic resonator chip looks at collective acoustic mode oscillations of 10 to the 18 atoms coupled to a superconducting qubit, which allows you to produce non-classical motional states, even Schrödinger cat states. And you can see this is 5 times 10 to the 17 atoms. However, the delocalization is only in the order of 10 to the minus 18 meter. And this is why also in that case, the product is at the end falls short by 18 orders of magnitude. What about the LIGO mirrors? You know, gravitational wave detector mirrors 20 kilogram objects. They must be great. They are not yet in a quantum machine, but they are close. So this is a 10 kilogram object, 10 to the 26 atoms. If you cool them to the quantum ground state, the delta X would be on the order of 10 to the minus 19. Okay, so let's assume they could do that. Then, well, look, there we are. It's then we would be 10 to the 1. However, I assumed now a hypothetical distance of 10 micrometer between the center of mass of two 5 centimeter large objects, which is nonsense, of course. Now we need to put 5 centimeters, and if we do that, we are back at 10 to the minus 11. So long story short, everything we have today, going up with mass, we go at the same time down with delocalization. This is the big problem. Right now, if I now put it in, let's call it gravitational cattiness, so exactly the parameter that I just showed you, mass times delocalization squared times Queen's time in units of h power g, we are many, many, many orders of magnitude away. This is the current status. So what should we do? The question is any of these systems capable of changing at least one parameter drastically? This is the question. And let's stick to the solids to begin with. These here, bulk solids and micromechanical devices, are clamped devices. So basically, the only thing I can play around with is coherence time. But coherence time enters linearly. There's no way I can increase coherence time by 16 orders of magnitude. Mass, well, mass enters quadratically. We already are at the Planck mass. If I have to add 9 orders of magnitude in mass, well, we are back to the LIGO mirror problem. Okay. Delocalization. Of course. Here the delocalization is 10 to the minus 18 meter. If I can get 90 dBs of squeezing, then I gain 18 orders of magnitude. Maybe that's the way to go. But here is the way I suggest. The way that I suggest is look at levitated particles. Why? What are levitated particles? It's essentially, I again need to now come to you, the atom physics community, which has trapped the particles. That's what we do. And why is that good? Because, well, we can trap the particles in an harmonic potential. We can use the harmonic potential to ground state cool the thing. So we purify it with a pure state wave packet. Then we switch off the trap. And then only on a short time scale, just by pure dispersion of the wave packet, we already get a much larger delocalization. Yeah, in that case, within 10 milliseconds, we already gain 10 to the 4. Factor 10 to the 4 in delocalization. So, and you could even, instead of just switching off the trap, you could even switch on an inverted potential, so you can even speed up the whole process and so on and so on. So these are all things, of course, that has been done already in wonderful atom physics experiments. But the point is now using that with solid state particles should open the way to really enter a parameter regime where we can up our gravitational cattiness, if I may say so. Okay, what's behind that? I'm carrying also to Athens. I still want to show it. Everything started in the 70s. January 26, 1970, the famous paper by Art Eshkin for trapping dielectric particles using radiation pressure. Then a couple of years later, there was in 86, there were these two papers, one that shows an optical dipole trap for trapping sodium atoms. And in the very same year, with essentially the same people, using the dipole trap for nanoparticles. And of course, in that case, it's a dispersive coupling detuned from resonance. In that case, it's also just a dispersive coupling due to the polarizability of your particle. You have an induced dipole, and then that's it. And by the way, so what came out then, of course, of the trapping of atoms, all the incredible experiments and many, many, many more. What happened after this paper, 86, in the domain of trapped solid state particle was nothing. Basically, well, people added liquid and did biophysics, but on the pure physics side, nothing happened. So here everything happened, and here nothing happened. Now, so this is what we are doing right now. So we have our particle, we're trapping it. Again, the physics is very simple. It's just an induced dipole. The potential landscape that the particle sees is just D dot E. D is the induced dipole moment due to the external electric field provided by the laser, which means the overall energy potential landscape is given by the polarizability times the intensity. So if I have now a Gaussian distribution in intensity, the potential is simply the negative of that, which means that I have for small displacements, a 3D harmonic confinement of my particle in the focus of a laser beam. And this is what you essentially see here. The particles that we typically trap are 150 nanometer glass particles, and then we bring them into vacuum. So here's one example. How do you bring them into vacuum? Basically, you see there's a nebulizer, just an asthma spray where you spray particles from a liquid solution into a vacuum chamber. You trap it then in the standing wave of a system that is connected to a hollow core fiber. Then what you do is you just switch on your optical conveyor belt such that the particle is transported from the high pressure loading chamber into the UHV scion chamber, where it's then picked up by another trap. And what you can see here, this is the hollow core fiber, and this is the particle that goes from the loading chamber, like here, zip, and goes into the science chamber, where it's then transferred into the other trap. This is actually a very nice method. The next thing, once you have it in the trap, once you have it in the trap, you basically put a cavity around it. There you go. So here's your particle. Here's your particle in the dipole trap. Then you put a cavity around it. The cavity is empty. Your tweezer here, that the dipole trap is stabilized with respect to the cavity. So what you do is you again detune your tweezer such that only the anti-Stokes scattered photons in your Raman setting process are resonantly enhanced. This is essentially laser cooling via coherent scattering into a cavity. This is a method that has been suggested in the early 2000s independently by Vuletic and Chu, the cool molecules where you don't have access to any internal transitions, and by Helmut Ritsch in Innsbruck back at the time. And this is essentially an implementation of that method. And we were able, just by holding the particle into an empty cavity, to cool the center of mass motion along the cavity axis into its quantum ground state of motion. Right now, so back then, this was an experiment with a cooperativity of only 5. With our cavity, we still could cool down the ground state. Recent news from the lab, we now do have a cavity that was built up by Yuri Koroli of 500. This is right now becoming operational, and we already very anxious to see what this cavity can actually do for us. Now, there you go. Oh, yeah. One last mention, because I found that really we only saw it afterwards. The Eshkin paper happened January 26, 1970, And we later found out that our paper of ground state cooling, almost to the date, appeared exactly 50 years later. We only missed 4 days. But we only found out later, unfortunately. What we are also doing today is that cavity is has an extremely strong technological overhead. So what we have also done now is, so we come back, here's the laser. This is not quite delayed. This is the laser. Here we are trapping the particle in our vacuum chamber. What we have built now is a backplane imaging method, basically borrowed from biology. It's confocal backplane imaging, so you reduce all the noise. And basically, our detection method is now basically Heisenberg limited. So the back action precision product is only 1.7 times 1.7 times h bar, which means that we essentially have built a Heisenberg microscope. So that means we can now monitor the particle motion. We combine it now with a stochastic Schrödinger equation model that runs in the background. It's also called a Kalman filter. So we take the information, we do a Bayesian analysis of the data to predict the future measurement outcome, which means we reconstruct in real time the quantum trajectory of the particle in phase space. And by doing that, we can now apply a feedback electrostatically. The particle is charged. We do have electrodes, and we apply a feedback that stabilizes the particle now in the center of the phase space, aka quantum ground state cooling via feedback. Because we are Heisenberg limited, the only noise that we have is quantum noise, so the particle is in its ground state. We do have, by the way, an out-of-loop measurement to show that. We can do a sideband thermometry, so we just scatter off photons off the particle to show that we have an imbalance in the Stokes and anti-Stokes scattered photons, which allows us to independently confirm that the particle is in its ground state. And what you see here now, this is an image of a 150 nanometer glass sphere that is cooled in its quantum ground state of motion in our room temperature environment. And now the next thing that we want to do, we want to expand the wave packet. So the idea is simply switch off the trap and do a free fall of the particle. Free fall is always bad because free fall means you somehow lose the particle if you let it fall too long. So what we do is we do free evolution. We basically build a 3D version of a millikelvin oil drop experiment. So we have electrodes around the particle such that when we switch off the trap, stabilize the particle, hold it in its position for a certain amount of time, such that after the free evolution time, we can actually switch on the trap again and have not lost the particle. And for that, of course, you have to calibrate before the DC bias that you apply in all 3 directions. And as you can see, if you do it wrongly, then after recapture, you have strong oscillations, but you can find a DC bias in all 3 directions such that the variance is minimal after recapture, which means you have a good stable configuration. So we do that. And what you can see here is right now, because this is very preliminary data, just look at the red points. This is actually the anti-squeeze quadrature. So basically the extent now here of our position delocalization. And as you can nicely see, you get this quadratic increase. And here in that case, this is like 2 orders of magnitude increase after 80 microseconds in the variance of our delocalization. In principle, it should now also be squeezed by the same amount in the other quadrature. As you can see, the measurement is not really nice right now, but this is work in progress. But the point is the delocalization, this idea of just having free evolution actually works. Now, I basically don't want to use too much of your time. Let me just give you one more example. What we are also doing right now is that's actually, remember I said the whole thing needs to be cold in the future. Yeah? Now there are 2 options of having, so trapping the particle in the focus of a laser beam is not a bright idea to have the particle cold. You heat it up. So now you have 2 options. Either you don't trap it at all using optics. I'll show you that in a second. Or you trap it using optics, but trap it in a dark spot. So this is an idea that we have been following up. So the idea is essentially we want to trap the particle on the top of an inverted potential. Yeah, so instead of having it confined in harmonic potential, use an inverted potential and try to stabilize it on top. The particle is charged, so you can apply feedback. And the nice thing of an inverted potential from an optics perspective is, of course, it's an intensity minimum. So this is something that we are doing at the moment. So we are essentially, let me just show you the whole idea. I don't know if that works. The whole idea is, does it work? Yeah, exactly. So the whole idea is, you see, the particle sits on top of the unstable potential, and we are following the particle position and just feeding it back and stabilizing it on top of that unstable potential. And so this is something that you can see here. Blue is actually the position of the particle. If there's no stabilization, it jumps back and forth between the left and the right minimum of the unstable potential. And once you switch on the feedback, then you see that the particle is stabilized on top of the intensity minimum. And what we are doing right now is we're trying to implement Heisenberg limited detection for this degree of freedom, such that the feedback allows us to purify the state on top of this inverted potential. So this should allow us to actually have a particle in a dark trap in its quantum ground state of motion. The alternative, of course, is why don't you go into the cryostat immediately? That's something that we do in collaboration with Hans Hübel and Rudolf Gross, where we have now superconducting particles, and we levitate those superconducting particles inside a dilution refrigerator, just using diamagnetic levitation. We read out the particle motion by just reading out the flux modulation through a squid. And then again, we can do feedback. Here, the challenge is actually, first of all, in a cryostat, have a good vibration isolation. That is something that we have implemented by a three-stage pendulum vibration isolation. And at the same time now, the question whether we can get Heisenberg limited detection, that is actually an open question, and that I really hope to answer together with our friends at WMI in the upcoming years, because that would mean that we could transfer everything I showed you in the optics domain, quantum control and state expansion and so on, but now in a regime where we are cold in principle and the masses are, can be up to Planck mass and so on in principle. Okay, last point that I would like to mention, we have not talked about gravity. So let's talk about gravity. What about gravity measurements? Remember, what we want is we want to have small masses, and we want to know that we can isolate gravity for small masses at short distances. So we started a couple of years ago to look into that, and what we did was we essentially tried to measure as an exercise for us the gravitational field of a 1 millimeter gold mass. So that's a 90 milligram object. The smallest objects so far were more in the gram regime and way beyond. And our question was, what are the experimental difficulties when you try to isolate gravity for small objects? Well, it is a completely natural question to ask. Well, and it turns out the most difficult part is, of course, electromagnetics and seismic isolation, so the environment, because at the end of the day, you see, we built a miniature version of a torsion balance of a Cavendish experiment. This is like 4 centimeters long. There's also a millimeter gold mass, and what you're measuring is essentially just displacement of that gold mass due to gravitational coupling to another gold mass over here. Now the question is, if you just measure displacement of the pendulum in the absence of any gravitational coupling, how does your response of the pendulum look like? And here you have the amplitude response as a function of frequency and time. And you see blue is actually nothing and yellow is a lot. So what you can see here is there's a resonance here at approximately 10 millihertz. Right? So there's a lot of excitation at 10 millihertz at any time of the day, which coincides with the traffic light cycle as the road crossing of Währinger Straße and Nussdorfer Straße, like 70 meters away from our lab. And you see the higher orders of that. Okay. And then what you see is that these black dots, this is between midnight and 5 a.m., where there is no traffic. Simply, the trams stop, buses stop, and so on. So this is actually the windows to measure in. Right? But then what you also see is there's always 1, 2, 3, 4, 5 dark spots, and then there's 2 less dark spots. And this is Friday night and Saturday night when people are actually out on the street during the night. And Sunday they're back home, and then we have 5 5-hour slots a week where one can actually measure. So in our case, what we did then, we waited until Christmas, and then during Christmas, we basically, you see here, this is our 1 millimeter gold mass. The idea was now you just do a position modulation here of a few millimeter. The minimum distance to the other sphere was 400 micrometer, and the overall acceleration modulation due to gravity on that side was on the order of 10 to the minus 10 meter per second square, corresponding to a few nanometer displacement variation and modulation. And this is what we actually picked up here. And you see in the force response, there's a nice response corresponding to the expected gravitational signal at the modulation frequency. And there's also a higher order, because what you do is you modulate a nonlinear potential. It's a 1/r potential that you modulate. And so obviously you have to be higher orders also in the response of the pendulum. So the accuracy that we managed to achieve in the experiment was 10%, which is okay because we did not plan to have a precision experiment. And this was all within the systematics of our experiment. And the precision was nice, was on the order of 10 to the minus 12 meter per second square. So there was a 1% precision level. So this is actually a quite nice sensitive method. So what comes next here? We understand now how to isolate gravity for millimeter-sized objects. The next thing is we make our mass, our source mass, smaller. So right now, basically where we want to go is somewhere in the 100 micron regime. And for that, we need to go outside of the city. And we have now installed our experiment, currently installing our experiment in this underground facility, 70 kilometers southwest of Vienna. And it's really quite nice and calm. So you see here, blue is the daily variations of seismic noise in the city. It really varies by 2 orders of magnitude. And red is during the same period in our underground facility, where basically you don't have any variations at all. Magnetic noise is much smaller, and so on and so on. So we are quite confident that now here with this our source mass microfabricated silicon cylinder that now sits on this disc that rotates in front of our Cavendish type torsional resonator. Last but not least, we are also setting up right now an experiment where we decrease the distance further. So we would like to go down to 10 micrometer. The shortest distance so far for which gravity has been measured is 50 micrometer. And this was an experiment in Eric Adelberger's group, the famous Earthwash group at the University of Washington. And Eric claims that that basically they were limited due to mechanical motion and patch potentials and so on. And we would like to see whether we can get rid of that in a more quiet environment with a modified experimental apparatus. And so right now we are setting up an experiment where we are trying to go down to the 10 micrometer regime in gravitational coupling, which is interesting also from a high energy physics perspective. It seems that several people in the community, both from the quantum field theory community and the string community, they actually expect that hidden dimensions that they expect in their models have to show up at some distance in gravitational measurements and short distances. And this is also a method to actually bound those models further. Yeah. With this, let me conclude. I wanted to show you why quantum sources of gravity are an interesting experimental endeavor to pursue. And so why? Because we want to create phenomena in the lab that a classical theory of gravity cannot any longer explain. This is the actual goal. And in order to do that, we need to have quantum sources of gravity. How? Well, basically, we are inspired by the early ideas of Feynman and now go into the modern day of quantum controlled solids, where we think that the requirements for large mass, extreme delocalization, long coherence time, and sensitivity to gravity can be realized. The way we do it is by combining a bottom-up approach, where we basically start with nanoparticles where we already have quantum control, and now try to grow them in size, in mass, and coherence time, combining with a top-down approach where we measure gravity for smaller and smaller particles at shorter and shorter distances. We have sort of a little, in our labs, sort of a little roadmap in form of food labels. You see for the quantum experiments, there are 3 parameters: mass, delocalization, coherence time. The mass we want to push up to 10 to the minus 4 Planck mass. Delocalization we want to push up to a few hundred nanometers. Coherence time we want to push up to like 10 milliseconds. So all of that needs to be green. The current green is our actual experiments at the moment. And the same for gravity experiments. The mass we want to go down to 10 to the minus 4 times Planck mass. Distance down to 10 microns, and acceleration sensitivity, acceleration noise down to 10 to the minus 14 meter per second square. So all of those need to be green. This is what my team is actually working on and working for. And let's say each additional bar is an order of magnitude improvement over both macroscopic quantum experiments and gravity experiments that exist. So each little step is already very exciting to be able to push further. So last summary statement, just to be very clear now, what do we learn from observing entanglement generated by gravity? Now let's assume one would observe it eventually. Well, to be very, very clear, because there are many misconceptions, I would claim, in the literature. So the generation of gravitation-induced entanglement is inconsistent with assuming gravity is described by a classical field theory. I think this is the one and only statement that you can correctly say. It does not tell us anything about the quantization of gravity. It is consistent. If we see entanglement, it's likely consistent with a low energy linearized quantum field theory of gravity. But it does not tell you whether there exist gravitons, whether loop quantum gravity is correct, whatever, we don't know. It excludes by principle all gravitational collapse models. And if you were able to do the experiment in the presence of retardation, so if you can really do it in space-like separations such that the gravitational field would have to propagate, then you would actually have how to say, a foolproof case for making a positive statement about quantum gravity. But I also claim this is an impossible experiment. Okay, so with that, big thanks to my group, who is really amazing in pushing all our food label green bars higher and higher. And also to you one more time, thanks a lot for having me, and thanks for the attention.
Thank you, Markus, for your fascinating insights. So the floor is open for questions. Immanuel.
Okay. Yeah, thanks, Markus, for the great talk. I have many questions, but I'll just ask now a few. We can talk later. Yeah. But so in the cooling, actually, I wasn't sure, is it 3D cooling or 1D cooling actually that you're doing to the levitated nanoparticles? And does that matter? Do the other degrees of freedom matter as you expand the wave pack and eventually want to do entangling experiments? Does it eventually have to be a true single mode expansion in all 3 degrees of freedom for the entangling experiment?
Okay, thanks. So what we did show is 1D cooling along the cavity axis. We can achieve 3D cooling. Basically, you can have effective cooling along the other 2 degrees of freedom, not simultaneously 3D. Actually, Francesco Marine's group has shown simultaneous 2D cooling, so that with using the cavity ground state cooling, so that's possible. For the let's say ultimate experiments where you want to entangle the 2 objects, we think it's sufficient to only have 1D ground state cooling and sufficiently confine the other 2 degrees of freedom. So basically, if you keep them at like 10 to 100 phonons or so, situation should be okay. So we are right now in the middle of sort of seeing the limits already in the expansion, actually, right? Because if you do 1D expansion, let's say in Z, but you have a large thermal excitement in X, then of course the free evolution does in the end mean that if you go in X too large, then you will also fall out of the trap. Yeah, and so these are the things we're currently testing. But right now it seems that 10 to 100 phonons in the other directions is sufficient to live with, and that is actually quite easy.
So when you modulate your masses, right? I mean, you're kind of detecting a gravitational wave in the near field. Is there a chance to see shot noise?
No.
That would,
yeah.
That would point to gravitons, right?
So now we're talking about the Cavendish type experiment, right? So so the short answer is no. The long answer is that first of all, you need to see that in the picture of basically gravitational wave coupling, the efficiency of the coupling is like, I don't know, 10 to the minus 30 or so, which means that basically in order to be able to see shot noise, you would have to be able to see fluctuations on top of a very large coherent excitation with a detector efficiency of 10 to the minus 30 or so.
You have a resonant detector, right? That is.
Yeah, that's called a Weber bar. I agree.
That would have a much higher efficiency, wouldn't it?
Yeah, but again, the fundamental no, even a Weber bar is maybe you gain by the Q factor. Yeah, so you go from 10 to the minus 30, you go to 10 to the minus 23 or so. So the fundamental problem will remain that simply the coupling is too weak to make that simple. So to make the full analogy to quantum optics.
It's as complicated as your experiments.
It's more common. No, like graviton. I really think gravitons are out of reach because of this fundamental mismatch between the analogies of quantum optics. Yeah. This is much more simple compared to what you were proposing.
Yeah, beautiful results. I'm always impressed by the precision experiments. Actually, one question was already addressed. My question was also, could you go from a torsional balance to a torsional oscillator? Because then you would gain the Q factor in sensitivity. This is actually what Doll and Neubauer did when they discovered flux quantization. They exactly did this, going from a balance to an oscillator. Has that been discussed already? Of course, you would need to send two masses at both sides and an oscillating drive, but then you could gain by the quality factor of the torsional oscillator.
Yeah, this is a longer discussion. I would like to see that you really gain by the quality factor, because in the end it's a signal to noise question, and you also amplify the noise. So the signal to noise stays the same. The signal so definitely you get a larger signal, but the signal to noise stays the same. So in our case, we deliberately stayed away from the resonance. So the resonance in the Cavendish experiment was like 6 millihertz or so, and we deliberately drove at 13.7 or so. So basically in a regime where variations in the drive frequency around the Q factor would just start to modulate exactly your signal, and then introduce. I guess the added difficulty in stabilizing it on resonance, and to me not clear whether you really gain on signal to noise ratio sort of makes it favorable. At least for us made it more favorable to measure off resonance.
And the second thing was, you didn't address the coherence time. When you go from very small or atom-like structures to solids, you usually have a large number of internal degrees of freedom. Is it already known how is the coherence time affected when you are going to bigger and bigger masses? Because if you getting worse and worse coherence times, then you would again not gain so much.
Yeah. So there are
these two-level fluctuator stuff, and you can have so many effects going to big masses.
So the initial motivation of our group to go to levitated systems was not gravity, that came later, but was to get away from the internal losses in the material, because I did not want to have to deal anymore with two-level fluctuators and clamping loss and so on. And so this was the original motivation. So, but now coming to the trapped particles, what are the natural sources of decoherence? Natural sources are obviously blackbody radiation. And there, of course, the larger you get, it scales dramatically. So this is why there are requirements in keeping it cold, actually cold, also the environment, both and the object. Then the next one is pressure. They are also in the action with the background gas scales with R square. And if you say it's a typical mean area for an atom, let's say, is of a few nanometers, then now if you go to micrometer, you immediately see how lifetime or pressure requirements scale quadratically. And then the next, but these are the obvious ones that lead to these requirements below 10 Kelvin, 10 to the minus 16 millibar or so. So I think that's something that is not totally crazy. It is crazy, but not totally crazy. And the question is now, what about other things? What about rotations? What about some internal oscillations and so on? There, my claim would be, as long as those degrees of freedom don't couple to position, you are fine. Like similar in Markus Aspelmeyer's experiments for the macromolecules. And even if they rotate and do stuff, they do the same stuff whether they are here or whether they are there. So as long as they don't radiate too much blackbody radiation, those degrees of freedom just factor out in the whole thing. This is my hope, but that needs to be seen. Actually, it's not totally obvious.
I have a related question, Markus. So regarding your millikelvin experiment, when you delocalize your particle, so what is the requirement on the electrical field homogeneity? Because I imagine if you have unique charges on your particle in order to levitate, so kind of to compensate gravity. So is it kind of clear?
No, I would say given the numbers that I showed you with like a few hundred nanometers maximal delocalization, the field homogeneity requirements will not be so much different from regular ion trap experiments.
Okay. Yeah. And is it basically a kind of test bed for doing the experiments in a gradient potential? So if you have a electric field, an inhomogeneous electric field, can you kind of test? Can you use this as a test bed for your experiments?
Yeah, that's possible.
There was a question.
You in the beginning you mentioned briefly the possibility of using a clock as a test mass and then sensing the time dilation caused by the source mass, right? And you concluded that the sensitivity you need is like 10 to the minus 30, so like 10 orders of magnitude away. However, you fixed the parameter of the distance of the clock to the source mass of what was 10 microns. So what's the prospect of decreasing this number? So if you get closer, I guess you also decrease the required sensitivity of your clock.
Yeah. So I had a similar discussion just last week with Junyi exactly about that. So why the 10 micron? It's very simple. I assumed a Planck mass object, which means it's like a 10 micron sphere, essentially. Right. And plus, I still claim that you will have to have a Faraday shield somehow. You need to shield electromagnetic interactions. And so you also need space. So 10 microns is sort of the minimum requirement. This is why also, even if now, for example, at one point in the future, we have nuclear clocks stoichiometrically in a sphere with Avogadro numbered clocks, and then you have 2 of them, and then you basically want to entangle your nuclear clock ensemble, right, via gravity. Also, then the 10 microns stick because you still need a Faraday shield, because otherwise you just entangle them otherwise.
So I have a question actually on the one limit that you described, which is the fact that your spheres start heating. So I guess this has to do with the fact that they are high field seekers. Is there actually any surface treatment or anything you can do to make them low field seekers, so you could actually trap them, for example, in a lattice in the minima or something, in a intensity minima, and would that actually help?
So I mean, the one method that we are proposing is basically actively stabilize them in a minimum. Yeah. So on top of the inverted potential, which is not a genuine low field seeker, of course. There have been proposals actually with hollow shell, so with shells, so hollow spheres. Actually, the problem there is, of course, you lose mass. So you gain potentially, so you can then work with with resonances. So okay, long story short, none of the proposals I have seen sort of circumvent the problem that you heat it up.
More questions?
Great, thanks. I was wondering, so you mentioned that you went from spheres to cylinders when decreasing the mass. So are there some challenges involved in going from this spherical shape to this cylindrical shape? For example, like stray electric fields, I can imagine, from this sharp edge.
So that's a good point. Again, we try to avoid electromagnetic interactions in general by having a Faraday shield. So for all gravity experiments, we always use a Faraday shield that basically shields the electromagnetic interaction and basically only lets the gravitational interaction survive.
So then kind of the cylindrical shape doesn't produce any further challenges. Yeah.
We have not seen it yet. I have to admit. So yeah.
Okay, great. Thanks.
Oh, I see no further questions. Was there a question from the Zoom? Okay. Then let's thank Markus again. And thank you for coming. Please, one request. If you haven't done so, please sign the sign-up sheet. Thanks.